Hello, this time having a look at some level 3 dividers questions. I'll get the first question up. Okay, right, this is one where it's helpful to have a list of the E24 values next to you when you try and solve problems like this. We've got a current divider and we're asked to make sure that the ammeter reads 2.914 milliamps from a current source of 6.5 milliamps. And this is done by the following method. Firstly, if we consider the standard current divider equation, then that would tell us that the ammeter reading, in this case 2.914 milliamps, is equal to the source current, here 6.5 milliamps, multiplied by the resistor the ammeter is not connected to, that's this one. I'll call that one R1 for now, divided by the total resistance, which is the sum of the two resistors. I'll call this one R2. And that gives me this equation here. Now you'll notice that this equation is one equation with two unknowns in it. So we cannot determine the two unknowns uniquely from this equation. However, we can work out their ratio. If I divide top and bottom for this side of the equation by R1, what I'm left with is 2.914 milliamps equals 6.5 milliamps divided by 1 plus R2 over R1. Now, if I take this up here and move this term down there and then subtract 1 from both sides, I would end up with R2 over R1 equals 6.5 divided by 2.914, since the millis cancel, minus 1. And I can work that out with my local friendly calculator, and that would give 6.5 divided by 2.914 minus 1 is 1.231. Okay, 1.231. So that's the ratio of the two resistors. I know that R2 equals 1.231 times R1. And what I'd need to do now is find two E24 values which, when divided by each other, give me that number in that ratio. This can be a process of trial and error, although if you have an Excel spreadsheet, you could set one up so that as soon as you work out this ratio here, you can calculate for any E24 resistor here what the corresponding value of R2 must be, and then just look down and see which one of those is an E24 value. Here, I could go through a trial and error process, and what I would end up with is noticing that if R1 is set to 1.3 K, for example, so R1 was 1.3 K, then that would work out to be, do it down here, you can see what I'm doing, 1.231 times 1.3, 1.6 K in this case. And 1.6 K is an E24 value. You may have to try a few different values of R1 before you find one, if you haven't got a spreadsheet set up, but that indicates that a valid solution to this problem would be R1 equals 1.3K and R2 equals 1.6K. Of course, it could be 13K and 16K or 130K and 160K. As long as the ratio is 1.231, that's okay. So, go back and try it. And to change the values of these resistors, you click on the resistor value, press delete, and then type in the value that you want. In this case, 1K3 for that one, and this one, delete, 1K6 for that one, oops, sorry, 1K6 for that one, and that should work. Yes. Okay, next type of problem. Okay, that's quite a straightforward one. We've got 21 millivolts here, as our V in, we've got 3.668 millivolts as our V out. So applying the standard potential divider equation, we've got V out, which is 3.668 millivolts, equals V in, which is 21 millivolts, multiplied by the resistance that we're measuring the voltage across, which is 910k, divided by the total resistance, which is 910k plus this unknown resistor that I will call R. So that is the equation that I'm trying to solve for R. And that's fairly straightforward. Just multiply this up here, bring that down there, and subtract 910k, and we get R equals 21 millivolts times 910k divided by 3.668 millivolts minus 910k. The millivolts cancel. That just gives me, well, work out that fairly quickly. 21 times 910k divided by 3.668 minus 910k is, that's, let's see, 4.3 million, or 4.3 mega ohms. You could use the calculator built into the quiz app, probably work better than this one. Let's have a go at that then. 4m3. Fine. That was fairly straightforward. Next one. Okay, this is a more interesting type of question perhaps. This is one with two current sources in it and two resistors. Now, the best way to solve these is using the principle of superposition, which states that you can set one of the current sources to 0 and then solve the circuit with the other current source, and then set the first current source to 0 and solve the circuit with the other current source, and then the voltages and currents at all points in the circuit will be the sum of the voltages and currents due to both of the current sources. That would be much clearer if I work through the example. Let's see, we've got here a 680 ohm resistor, an unknown current source A ammeter, which is reading something, a resistance here of 3K3, and a current source down here, which is 28 nanoamps. Right. First thing, let's ignore this current source here. Oh, another thing I need to know, which way round is the ammeter? The ammeter is red terminal here, black terminal there, so it's measuring the current in that direction. Okay. Right, ignore that current source for now and solve for the current flowing through the ammeter. And the answer is, well, standard current divider equation. The current flowing through the ammeter in this case would be the current input, A, multiplied by the resistor that you're not measuring the current through, 680, divided by the total resistance, 680 plus 3K3. And then put this current source back in and forget this one and work out what the current through this ammeter would be. And this time the answer is, well, the input current here, 28 nanoamps, multiplied by the resistor that you're not measuring the current through. Now that would be this one, 3K3, divided by the total resistance, which is still 680 plus 3K3, and note that now the ammeter would read this current as a negative current, because the current would be flowing that way through the ammeter, not in the direction that the ammeter is set to measure positive currents. So that would be minus. And the principle of superposition tells us that the total current through the ammeter will just be the sum of these two. So that is 680 times A minus 3K3 times 28 nano divided by 680 plus 3K3. Okay, let's try that. 680 times A minus 3K3 times 28 nano divided by 680 plus 3K3. And note that the question is asking for an expression in terms of the source A, so it's expecting to see something with the value of A in it. Fine. Okay, is that enough? Maybe try and do one more. Okay, this one is another given expression one, but this time it's with voltage sources, not with current sources. But we can use the same kind of technique. We can do it by the principle of superposition, considering two circuits, one of which only has this source in it, and the other one only has this source in it. If I set a voltage source to 0, that means that there is no voltage between this point and this point in the circuit, so effectively there's a wire connecting them. They're always at the same voltage. So, the circuit with only the source A in it effectively looks like this. A comes up, we have a 470 ohm resistor. That goes through a 330 ohm resistor, goes back down to the bottom of voltage source A, and the voltmeter is measuring the voltage across this resistor, the 330 ohm resistor. So that is the equivalent circuit of this, or at least it would be after I write in the values of the resistors. All I've done is move the components around a bit to a more familiar potential divider shape and set that voltage source there to 0. Then there's another circuit that I could make where I leave this voltage source as 0, so effectively connect this point to this point with a wire and treat this one as 100 millivolts. And if I draw that equivalent circuit in the standard potential divider form, I would have this point here as the bottom of it, would go up through the 100 millivolts, come down through a 330 ohm resistor into a 470 ohm resistor, and back down round to the voltage source. The voltmeter is now across the 470 ohm resistor, but this time the voltmeter has its positive terminal in this direction down here at the junction between the 470 ohms and the 100 millivolts voltage source. So these are the two circuits that I get by considering just one of the voltage sources each time. Applying the standard potential divider equation to each one, this one would give me a reading on the voltmeter of A times 330 divided by the total resistance, 330 plus 470, which is just 800. I can do that in my head. And then here, the voltmeter would read, well, 100 millivolts is the input, times 470 divided by the total resistance, 800. But this time it's negative because the voltmeter is this way round with its positive terminal at the bottom. Principle of superposition tells me that the total voltage that the voltmeter would read would be the sum of these two. So, total voltage is 330 times A minus 470 times 100 milli divided by 800, and that should do. 330 times A minus 470 times 100 milli, which is just 0.1, divided by 800. They are quite a bit harder than level 2 and level 1, but they're level 3. They're supposed to be. Good luck.